Hi, this is Martha Moody again. We're going to talk about Week 2, Part 2, Page 1 on your lecture notes. Please refer to those lecture notes for the corresponding page numbers in your textbook. First of all, we're going to have an introduction to polynomials. We'll talk about addition and subtraction, and then we'll go ahead and talk about multiplication. I will not ask you on a test to identify what a polynomial is, but you will be expected to work with them. The definition of a polynomial in one variable is an expression of the form as you see right here underneath of it. These a sub n's refer to the coefficients. So down below you'll see they're like the numbers 2, 3, minus 3, 4, and so on. The x to the exponent refers to, this one starts out with n and n minus 1 and dot 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 and goes on forever, and then a 2 and then a 1. It can have any of those exponents, or it could actually have none of them. So this example here has an x to the 5th and an x to the 4th, an x to the 3rd, an x to the 2nd, and an x to the 1st. You could drop out any 4 of these or any 2 of these. It doesn't have to be any definite expression where it goes down in descending order. And then the last thing that you see is an a sub 0, which is just a number. So these a's are any real numbers, and the x's are your variables, and the numbers up in the air, the exponents, are the exponents that go along with them. So again, the n, the number up in the air, is any non-negative integer, and so that means it could be a 0, 1, 2, or a 3. It could not be a negative number. And the a through n through a through 0 are any real numbers, and where that coefficient is not equal to a 0. So examples of polynomials in one variable are the ones that you see right here. They don't have any variables in the denominator. They don't have any non-whole numbers or non-negative integers in the exponents. These are examples of ones that are not polynomials in one variable, because the first expression has 2 variables and the second one has variables in the denominator. Polynomials in several variables look like these two. So again, they follow the rules that the other one did, where you don't have any variables in the denominator. So the next thing we're going to talk about is the definition of a term. A term is a real number, a variable, or a product, which means multiplication, or a quotient, which means division of numbers and variables. Terms are always separated by plus or minus sign. So the first expression that you see there has 3 terms. The first term is 5x to the 2nd. The second one is minus 3xy, and the last one is negative 7. The sign always goes with the term. You have to use that sign that's in between them with it. So the question is, how many terms are in the following? So the answer is going to be 4. It's negative 1, positive 3x, negative 4xy, and negative a. A numerical coefficient is a number used to multiply a variable. 6z means 6 times z, as we discovered from the first week in class. Z is the variable, making 6 be the coefficient. Variables that have no displayed number have a coefficient of 1. For example, x is really 1x, so the coefficient is a 1. In the example that we have here of 4x to the 2nd y plus x, 4 is the numerical coefficient of the x squared y, and 1 is the numerical coefficient of the x. Going on to page 3 then, again, the coefficient does include the sign, so of our example that we have here, 8 is the coefficient of the x to the 3rd power. Negative 12 is the coefficient of xy squared, and 1 is the coefficient of y. If the negative isn't there, it is a plus sign, and you might want to put the plus sign with it. The next example that we have is minus 3 is the coefficient of x squared, minus 1 is the coefficient of the y, and 0.5 is the coefficient of the y squared. Typically, polynomials are written in descending order of the numerical exponents. So we would generally write the expression that you see on the first line here. It would typically be written as minus y to the 8th power plus 1/3 y to the 4th plus 5y to the 3rd power plus y squared minus 1. So those exponents go in descending order. The 1/3 that you have right here, 1/3 is meant to be the coefficient, and it's the coefficient of the y to the 4th. The y to the 4th is not on the bottom of that denominator. Special polynomials, like monomial, it has one term, so it would be 5x or 5y squared. A binomial, like a bicycle, has two terms, y to the 2nd minus 1. A trinomial is like a tricycle, has 3 terms, as the example here has. Like terms are something that's very, very important to what we're going to be doing for addition. Like terms are terms with exactly the same variables, that means the same letters, and the same exponents of those variables. For example, 3x and 7x are like terms. So if you cover up the 3 and the 7, you can't tell any difference between those two. They're identical. On problem number 2, 3x to the 2nd minus 2x to the 2nd, those are like terms because if you cover up the 3 and the minus 2, they're identical. You can't tell the difference between them. On number 3, we have 3 terms there, and if you look at the last term, we can actually turn the z to the 3rd power y to the 2nd around and write it in alphabetical order, and then they all look totally alike. We can do that because the commutative property of multiplication, which means that we can turn 2 times 3 is equal to 3 times 2. So it's also true for the letters. So if you cover up the 2, the minus 7, and the minus 5, those are identical. They have to have all the same letters, and each and every one of those letters has to have the same exponent. So examples are, let's take a look at something. So if I ask you to add 3 apples and 2 apples and 4 oranges and 11 oranges together, you would match up the apples and tell me there were 5 apples, and you would match up the oranges and tell me that there are 15 oranges. So if you look at what you've done, you've added the 3 and 2 together and you've left the apples alone. You haven't changed them to apple squared or anything else. You've left them as apples. Same thing with the oranges. You've left them as oranges. So going on and taking a look at this with x's instead, so we're going to let the x's be the apples and the x squared be the oranges. So we're going to match them up identical to that. So we are going to have 3 plus 2 gives us 5, and apples stayed apples, so x's stays x's. We just have more of them. We have 4x to the 2nd power and 11x to the 2nd power. We add the 4 and 11 and get 15. We keep the x squared the same. Doesn't become x to the 4th or anything else because those were oranges. They're now x squareds and they have to remain the same. If we look at this expression right here, if we cover up the 2 and the 3, the x and the x squared are not the same. That's all that you can do. If 2 terms are not like terms, they cannot be combined any further, so we just leave them alone. If you wanted to write this in the conventional order, you could write it as 3x to the 2nd plus 2x. But this way is the same thing. We can turn it around because of the commutative property of multiplication. So I'm going to stop the video at this point, and then we'll pick up on the next part.